Okay, so now we talk about the single source shortest path problem for proposed by Edgar Dijkstra or Dijkstra. Okay, so this is a single source shortest path problem, means we study from a single source vertex to all other vertices in the graph. Okay, single source shortest path problem. Okay, so we find the shortest path to all other vertices from a particular source. Like here, we have to find shortest path to all the vertices from the single source S. Okay, so now how this algorithm works. Okay, so this is an important greedy algorithm. And why is greedy algorithm? The objective, the strategy of this algorithm is very similar to the one we studied earlier for minimum spanning tree, which is the Prim's algorithm. And you will find what we do here, we maintain a set S of vertices whose shortest path distance, this is shortest path distance. Okay, so shortest path distance from S is known. Okay, so S is a vertex, small s the vertex belonging to the set capital S, and we are saying the distance estimate of the shortest path distance estimate of S is already known, the small s. So now at each step, add to the capital S, the big set, the vertices which belong to V, belong to V minus S, and whose distance estimate is minimum. Okay, so among all the vertices in the set V minus S, you check whose distance estimate is minimum. Pick out that vertex and add it to the set S. Okay, update distance estimate of vertices adjacent to V. So we will show you the algorithm is very similar to the Prim's algorithm, and we'll walk through this algorithm on this example graph. Okay, so initially what we do, initialization is this step. This is very similar also to Prim's algorithm. Is a priority queue, have all the vertices in the graph, and there is a set S which is initially null. Okay, there is no vertex in the set S. Now after some time, there is the distance estimate of all the vertices initially are infinity. So so these are all infinity distance estimates. Okay, so infinity and infinity. Okay, so now select an arbitrary vertex S and make the distance estimate of that vertex to be 0, and then we put that vertex to the set capital S. Okay, so here so that will be the next step. Let's see here. So what about the priority queue? So the priority queue, let me write the priority queue. This is A, this is B, this is C, this is D, and this is E. Okay, so what we do initially, all the this is the queue. Okay, so initially all the distance estimates are infinity. So the shortest path distance is not known. So the distance estimates are infinity. While q not equal to phi, so before that, let's do this. The shortest path distance estimate of a starting vertex, any arbitrarily chosen, or if it's given and by the problem, that's also fine. So the ds is 0. So assume that because it's alphabetically ordered, let's make this one 0 and the starting vertex. So this is 0 and all other infinity. So while q not equal to phi, extract the minimum from the priority queue. The minimum distance estimate is the a, which is this, and so we take it out, and and then what we do, we put this vertex to the set S, capital S. Okay, so then for each vertex adjacent to U, that means this vertex S, the starting vertex, what we do, if dv greater than du plus wuv, distance estimate of v, that means B and C are greater than the du plus wuv. Du is what? Distance estimate of u is 0 now, and 0 plus 10, is it less than infinity? That is the question. Okay, so distance estimate of vertex V, which is B now, is infinity. It is greater than distance u, which is 0, plus wuv, the edge connecting u and v, which is edge weight 10. So yes, that is true. Then what we do, we update the distance estimate of v with the distance estimate of u summed with the edge weight. So now this is 0 plus 10, so this is changed to 10. So here B's distance estimate is changed to 10, and similarly C's distance is changed to 0 plus 3, 3. Okay, C's distance estimate is 3. Rest of them are infinity because they are still unreachable from the single source S. Now you see here this step, what it does, it is actually reducing the distance estimate of that particular vertex reachable from the source. Now every step we can pretty many times we can do this operation of reducing the distance estimate, and this step is called relaxing an edge or relaxation. Okay, relaxation. So the edge relaxation, and we keep repeatedly doing the edge relaxation, and finally when there is no relaxation possible, we will know that the final distance is actually the shortest path distance for that particular vertex from the source vertex. So the relaxation is actually tries to find out all possible paths and checks adds the distance estimates and finds out through which path we can reach to this vertex with the cheapest cost, and that's why we can do multiple times until there is no further reduction is possible. Okay, now you see we keep doing the same thing again. Q is non-null, so extract mean among this. 3 is the minimum. Okay, so come here, highlight C, that means you take out C and put it to the set S. Okay, so C is out now. So we will check all the vertices which are adjacent to C, but not in the in the priority queue. So what we do? So we check. This is B. We can go to B, and C to B is 3 plus 4, 7. You see 3 and 4, 7. Now this is 10. So this is more. So we replace it with a cheaper distance estimate. You see A to B path was giving a shortest path distance of 10, shortest path estimate. And now we have even a shorter path through C to B, which has distance estimate 7. So we replace it. We relax the edge even more. Okay, so now B is 7, and now from C we can also go to D, which is 8 plus 3, 11. You see, this is 3 plus 8, 11. So D is 11. And what about E? You can also go to E, 7 plus 3, 10. So E is 10. Now we have no infinity distance estimate. Every edges we have at least one distance estimate. Now among this, we check which one is the minimum. The minimum is 7, which is B. Okay, we take out B, and you see there is a path from B to C, which is will not do that because C is already taken out, but I'm just trying to show you that now 7 plus 1, 8. That was the distance estimate through this path, but C already had a shorter distance estimate. So we are in the correct track. Now what we do, we see this distance is 7 plus 2, 9. You see from B to D there's a cheaper distance estimate. So we change 11 to 9 and write it here. Okay. So now this 9 and 10, these two are the one here, and because you cannot go anywhere else from B, so among this, the priority queue, 9 is the cheapest. So take out D, whose distance estimate is 9, and then you see the path. Okay, from 9 plus 7, you see there's a path which is 16, which is much more than this. So we do not change it. So we don't take that path. We took this path, we took this path, and then no, we didn't take this path. B's distance estimate was through this path. Okay, and then this was also this, because this is now the next minimum is 10. So we take out E, and from E you could have gone, which is 10 plus 9, 19, but we had a cheaper path, you see. So all our estimates are correct. 10 is now out. So from this graph we got the shortest path tree, which will be like A here. From A we go through this edge to C. From C we go to B, which is using an edge with 4. From B we go to D. Okay, from this edge, which is 2, and then from C we go to E. So this age was 7. So this is called the shortest path tree. Okay, shortest path tree, or SPT. So there can be certain nice question, brain teasing questions, that for a graph, what do you think? What are the relations between a shortest path tree and a minimum spanning tree? Do you think they can have ages in common, or they may not have ages in common? For different types of graphs, different properties, we can ask these questions, and you have to think about it. So please think about it. Now let's see the complexity of this algorithm, which is very similar to the Prim's algorithm. So the complexity analysis will also go on the same direction. So for this part, where you have this initialization where v vertices are put in Q and their distance estimate set to infinity, so this will run for theta v times. Okay. So now for this part where the priority queue is investigated every time and one vertex is taken out, so this entire thing will be run for theta v times. Okay. And so this theta v times, this extract mean operation will be done. So we put this here, the time is theta v times t extract mean, and this part, so like this part will be done, theta e times, because this is actually about the degree of u, degree of a node, and the degree of node by handshaking lemma is of the order of theta e. Okay, so theta e number of this is implicit decrease key again, implicit decrease key. Okay, so this operation is being done for theta e times, which is like degree of the vertex from the this v belongs to adjacency list of u. So now you see the total time is theta times v dot t extract mean, theta of v times t extract mean plus e times t decrease key. Now if we use the array implementation of the the priority queue, array implementation of priority queue, say the queue is implemented using array or queue is implemented using binary heap, queue is the priority queue here. You can see for the array you can find the minimum number as long as you go through all the elements, and then you can find the minimum. So it's a maximum. The worst case is order of v, and once you find a node, it's very easy to change the key value. Okay, so that's the constant time operation. If you use a binary heap, so the heapification and then the you take out the minimum, so that takes log v, and if you do the decrease key, you have to do reheapification, that will take another log v time. So now if you put those values in this equation of time calculation, you will find for array this is order of v square, and for binary heap is order of v log v, and order of v log v plus order of e log v. Okay, so e plus v, v plus e log v, or you can say of the order of e log v. Okay, so this is the idea of single source shortest path problem using Dijkstra's algorithm, which is a greedy algorithm. You remember the greedy algorithm's properties, and this is the pseudocode of the Dijkstra's algorithm. So we have analyzed this and did the time complexity calculation using array implementation of the priority queue and using the binary heap implementation of the priority queue. We have also shown one example run using the the status of the priority queue, and then we generate the shortest path tree from this graph, and which will give you the shortest path estimate from the source node S to all other node in this graph. Thank you.